I think the challenge of this, which is very often the challenge of most MCAT questions, is looking at it and figuring out, what am I supposed to do here?
Phil, back for some more MCAT podcast, Passage 5, full-length 1, Blueprint MCAT full-length exams. Oh, these are fun. These are hard. These bring back like PTSD memories for me going through this test, although it's on the computer and not paper, so it's a little different from when I actually took it.
Yeah, it's quite a bit shorter also back in the day. I remember when I took it, it was only 3 hours, and then it was 8 hours, and now it's 5 hours. So
we'll find a happy medium somewhere.
Yeah, we'll find something somewhere.
Yeah, that's the biggest thing that I'm interested in. Obviously, this as we're recording this, it's much earlier than when this actually releases. The plan is for this one to actually come out. Ooh, when is this one going to come out? June 10th-ish. So maybe after that first round of exams. My biggest question is how and why how can the AAMC go back to an 8-hour test if they're telling us that this 5-hour and 45-minute test is apparently good enough?
Yeah, that's going to be, I don't know. They probably don't care. Like if we all complain and moan and groan, like, why can't we take the 5-hour? They're not going to pay attention. I do think that there is, with a smaller thing, you have more variability. And so like there is a little bit less, consistency, just, you need more data. The more data points you have, the more confident you are in the answer. So maybe it's just a confidence thing on their side.
Yeah, not confidence as in ego, but confidence as in statistical data.
Right.
Confidence interval stuff.
Yeah.
Okay.
Speaking of confidence intervals, there's confidence intervals in this passage.
Who knew?
As we talk about potentiometric titration.
Okay.
So this potentiometric titration is a useful means of characterizing an acid. No indicator is used. Instead, the cell potential is measured across the analyte solution. When cell potential is plotted against titrant volume added, the equivalence point is the cell potential at the inflection point, the midpoint of the steep segment of the titration curve. So we got a lot of stuff going on here. There's a really, really good chance that you have never heard this term potentiometric titration. And I think I had never heard of it until I saw this passage. So they're telling us it kind of seems similar to like a regular titration where you like add base and you have an equivalence point and all of this stuff. But we're also adding in this ability to measure the voltage or the electric potential. And so that's why it's a potentiometric or potential measuring thing. And so that's telling us when we reach this equivalence point rather than looking at the actual, like indicator, like change blue, right? Like this seems like a little bit more precise. So for polyprotic acids, an acid hydrogen will produce an inflection point only if it is not very weakly acidic, and if its ionization constant differs from that of any other acidic hydrogen of the acid by at least a factor of 10 to the fourth. All right, they give us a number there. Might need to reference back to this. This is specifically for a polyprotic acid. So after this, we go into probably something that's a little bit more familiar landscape for you, Captopril. So it's molecular weight, they give it to us, and that's shown in figure 1 is a competitive inhibitor of angiotensin converting enzyme. So you have the Captopril molecule, which is going to be an ACE inhibitor, which is going to be useful for dealing with blood pressure stuff. But as I look at this, like we have this sulfhydryl group, this SH group, we have a carboxylic acid, we got this weird ring with a nitrogen. They always like to ask questions about these like biological molecules that they give us. And so like looking at this, maybe they're going to ask us a question like identifying some of these things. Like there's an amide right smack dab in the middle of this molecule. That's the double bond oxygen with the nitrogen. They end up not asking about it with this passage, which is why I'm talking about it. But that's something that like I would expect them to, that sort of thing is the sort of thing that they ask about. So students studying Captopril were provided the following in vivo IC50 values. The minimum plasma concentration needed to inhibit 50% of the target enzyme activity in vivo for Captopril inhibition of ACE under different pH conditions. So it's going to like take a second and step back I'm just going to talk about this IC50 thing. This is another topic that I think an MCAT student probably hasn't heard of, right? They're not really sure what an IC50 is, but the MCAT has been known to like throw this into a couple of things. It's a little bit unfair, but this is why it's on practice tests, so that you see it and you're like, oh, what is this thing? And you like go look it up, and then you can deal with it, on your actual test day. You're not caught off guard and blindsided by it. So the IC50 is the minimum concentration of whatever it is that we're talking about needed to inhibit 50%. So it's the inhibitory concentration at 50%. So if we look at this, we have the Captopril values for these different pH ranges, pH 1.5 to 3.7, 3.8 to 9.5, and 9.6 to 12.5, and these different IC50 values. So what's your kind of initial, like, looking at this, trying to interpret this data? How are you trying to take a look at that?
It looks like there's this weird kind of curvy thing with the pH range. So the lower pH, 1.5 to 3.7, this IC value is 0.058. In the middle pH range, it's much lower, if I can say lower, at 0.012. And then at the higher pH range, 9.6, it goes back to where kind of the other one was at 0.069. So it's got this weird curve of how that looks.
Yeah, definitely also looking at the figure up above. Note that they give us the pKa's for the sulfhydryl group is 9.8, and the pKa of the carboxylic acid is 3.7, which are those middle points in those pH ranges. They have the pH up to 3.7, from there to 9.6, and then above 9.6. So they're kind of telling us like what's happening at these different points as we're dealing with the molecule. So there's a couple questions I'm trying to anticipate, but like I'm not going to go too far because those questions actually do show up. One thing I do want to hit on is this IC50, right? Like, what does it mean if the IC50 is low? What does it mean if the IC50 is high? So IC50 is the amount of the drug we need to shut down 50% of the ACE enzymes. And so a smaller number is a more powerful drug because I don't need very much of it to shut down 50% of the angiotensin converting enzyme. So a bigger IC50 is actually a less powerful drug. And so that's something that seems kind of counterintuitive, where the smaller the number, the better the drug is. It just means you need less of it because it's telling you how much you need to shut down the enzymes. Okay. So we're not done. The passage keeps going, right? We go into this like actual graph of the potentiometric titration. So students then performed a potentiometric titration of captopril in order to determine the captopril content in the tablet formation. 2 tablets were ground and homogenized, producing 104.4 grams of fine powder. The powder was then dissolved in 100 mils of water and titrated with a solution of 2 times 10 to the negative 2 molar sodium hydroxide. The potentiometric titration curve obtained, along with a plot of the rate of change of potential during the titration, was shown in figure 2. And then we have this figure where we have the titration curve as we're adding in our sodium hydroxide. We can see kind of the traditional titration curve appearance, like that S-shaped curve. And then we have this sharp peak of the cell potential right around, I'm going to say like 7.5 or something like that, telling us that that's probably where the equivalence point is happening. Because remember, from the first paragraph, they told us that we get this kind of indicator through the potential when we hit the equivalence point rather than using an indicator. And so they give us that in figure 2, and that's it.
Yeah. So if I'm going through this, I'm like, C, next passage.
Well, remember, there's a lot of questions that you can answer, like maybe with outside knowledge and kind of reasoning, that sort of like logicking your way through problem solving, like even if you're a little bit lost, because I know your kind of responses is like, I don't know about potentiometric titrations, right? I am not confident in that. But to be honest, that's the same thing most students are going to be in when they see this kind of like potentiometric titration. What's going on here? And so they're not going to ask you like, how do you set up? What are the steps of like doing a potentiometric titration? You just have to, they give you something and then try to see how well you can deal with this using your outside knowledge and applying it.
Yeah. Okay, let's check it out. So question 23, Nice Michael Jordan number there. How many moles of captopril were present in the original analyte solution tested? All right, so the original analyte solution tested. Ooh. So we have answer choice A, 7.5 times 10 to the negative fifth moles. B, 1.5 times 10 to the negative fourth moles. C, 7.5 times 10 to the negative third moles. And D, 1.5 times 10 to the negative second moles. So all of the times 10 to the negative, those are all different. So that's something to keep an eye on. Two of the answer choices are the same, the 7.5 minus the times 10 to the negative whatever number. Okay. So the question is, how many moles of captopril were present in the original analyte? I don't know what the original analyte means, just based on what the passage. All I remember talking about here is the captopril content where they produced 104.4 grams of the fine powder dissolved in the 100 mils of water. Is that what they're saying is the original?
Yeah, so they're trying to figure out just how much captopril is in this container, how many moles of it is in the container. Okay. And they do this titration curve, and the titration is to figure out how much is there. So there must be some way to figure this out from the titration, because that's the whole point of a titration. And so the key here is that anytime you hit an equivalence point, the moles of the acid are equal to the moles of the base. And that's the point of the equivalence point, right? Yeah. Like it's equal, it's equivalent, acid and base.
And that's where that cell potential in this figure 2, you said, looks maybe about 7.5-ish, right?
Right, yeah.
What is that?
Like
sodium
hydroxide,
yeah. So if we add that much sodium hydroxide, then it's potentially saying the equivalence point is that's how much captopril is there as well. So 7.5 must potentially be the answer. So A or C. Now the question is it 10 to the negative fifth or 10 to the negative third?
So the problem is that 7.5 milliliters. That's not how many actual moles of the sodium hydroxide is in there. Right. So that's just how many like drops we put in there.
Yeah.
But they do give us the concentration of it.
Yes. So we have 100.4 grams in 100 mils of water.
And then we titrated that with the sodium hydroxide, which was 0.02 molar, or moles per liter.
Yeah. All right. I'll let you do the math.
So if we've got 0.02 moles per liter and the sodium hydroxide stuff, and we only use 7.5 milliliters of it, you can just multiply those two, because you got moles per liter times liters if you convert the mils to liters. So and then you're just left with moles. And so it's going to be 2 times 10 to the negative second molarity times 7.5 times 10 to the negative third once you convert that to liters. So 2 times 7.5 is 15. And then you end up with 1.5 times 10 to the negative fourth moles per liter when you convert that back to scientific notation. So the answer is B. This is one of those ones that I know we're kind of like going through in our heads. Definitely want to write this out. Right?
Let me just clarify. You're going through it in your head. My head is doing.
Yeah.
Yeah. Okay.
Yeah. And so, writing this out, like it's not as bad as it seems. It's just 7.5 mils times 2 times 10 to the negative 2 moles per liter. I think the challenge of this, which is very often the challenge of most MCAT questions, is looking at it and figuring out, what am I supposed to do here, right? Because there's a lot of stuff going on in the passage. There's a lot of things kind of happening. And so just kind of like falling back to like, okay, we did a titration to figure out how much captopril we had, so we must be able to figure it out from the titration. At the equivalence point, which we kind of know where that is, the moles of acid equal moles of base, so just how many moles of acid did I had? And go through it that way. All right, next question.
If the students perform an enzyme inhibition assay using captopril, which of the following changes in the kinetic parameters of ACE should be expected? A, Vmax decreased, Km unchanged. B, Vmax decreased, Km increased. C, Vmax unchanged, Km decreased. Or D, Vmax unchanged, Km increased. So, yeah, I don't know. How do you even start thinking about this? So Vmax, I'm looking, I'm like, Vmax, we didn't talk about Vmax, I don't think, in the passage. This seems like a pseudo-discrete where you just have to understand what happens with these changes.
This is going to go into some stuff with enzymatics. And so you have to know kind of how these different inhibitors work in terms of competitive and non-competitive and uncompetitive. And, not to get into a lecture, the passage here, they say is a competitive inhibitor. It's right underneath figure 1. They say, right above figure 1, where it says Captopril shown in figure 1 is a competitive inhibitor of angiotensin converting enzyme. So the Vmax is how fast this angiotensin converting enzyme can work at maximum speed. So generally you add an inhibitor and it slows down a reaction. The Vmax is like how fast can this enzyme work if it's working as fast as possible. I always imagine, the old I Love Lucy episode where there's like chocolates going by on the conveyor belt. Like there's a max speed that she can work, right? Like whatever that is, they went past it and like she's just like shoving chocolates everywhere. And so that's what I think about when I think about Vmax. It's Lucy's maximum chocolate wrapping speed, or converting angiotensin for angiotensin converting enzyme. Okay. Now, if you add a competitive inhibitor, that's going to compete for the active site with the angiotensin, because they're both going to go into the same thing. If I keep adding more and more angiotensin, my inhibitor isn't going to get a chance to get in there. It's like if you're trying to get in the Apple store and there's 10 million people trying to get in, it's like I'm being outcompeted because there's too many people trying to go for that spot. So that tells us that, like in this scenario of infinite substrate, this enzyme is still going to work as fast as it normally does. Its Vmax is going to be unchanged because the inhibitor is not going to get a chance to go in there and shut it down. And so the Vmax ends up being unchanged in order to, like, in the scenario of a competitive inhibitor. And so that tells us it's got to be C or D at that point, because we know that the Vmax can't be altered. Now, Km is how much substrate do I need to add to get to that 1/2 Vmax. So if I add an inhibitor, that's going to make it harder for the substrate to get in there. So I'm going to have to add more substrate than normal to get that to the half of its maximum speed. And so our Km, which is a measurement of how much substrate we need to reach our half maximum velocity, that's going to go up. And so the answer's got to be D from there.
Of course.
Of course.
So can you walk through real quick? And it's funny. A lot of students are like, why is Dr. Gray on this podcast? Like, Phil should just do it by himself. But I have I'm a dumb pre-med brain. Not all pre-meds are dumb. I'm not saying that. I thought you had said that the competitive inhibitor would cause the Vmax to decrease. Did you not say that?
So it will make it, so the Vmax goes, so the velocity will decrease when you add an inhibitor. But if you add enough substrate, then the inhibitor can't do anything, right? Like imagine that, I always like to use this analogy of like an Apple store. Like your job is to go in and shut down the Apple store. You're trying to inhibit the Apple store. You work for Samsung, I guess, in this scenario. A competitive inhibitor is going to try to get into the same spot that everything else is trying to get into. Yeah. A non-competitive inhibitor is going to go like in the back door and shut it down. And so the thing with a non-competitive inhibitor is it doesn't matter how many people are trying to get in the front door. Like you're going to be able to shut down the enzyme all the time. Okay. But in the case of a competitive inhibitor, if you keep adding substrate, eventually the competitive inhibitor, like if there's 10 million people trying to get in that front door and you're trying to get in to shut it down, you can't. Because you're being outcompeted because there's all that extra stuff. It's
like A Bug's Life when the ants finally realize that they outnumber the grasshoppers.
That's exactly it.
All right. That's what I'm here for. Okay, so it's not necessarily that the velocity can't decrease. It's saying the maximum velocity
is going to be
always be the same.
Because the maximum velocity is defined as the velocity when there's an infinite amount of substrate. And so with a competitive inhibitor, if you have an infinite amount of substrate, with or without the competitive inhibitor, it doesn't make a difference because the competitor can't get in there. The non-competitive, it can.
Got it.
And so, because you're shutting down the Apple store, it's just going in the back door in that scenario.
That is where I got confused. The only place I got confused. All right. A Bug's Life theory. There we go.
You're right.
Question 25. Have at it.
So which of the following protonation states of the captopril thiol and carboxyl groups is required to maximize captopril's inhibition of angiotensin converting enzyme?
Yeah. So go ahead and read those answer choices.
So we have a deprotonated thiol and protonated carboxyl, a protonated thiol and deprotonated carboxyl, deprotonated both thiol and carboxyl, or protonated thiol and carboxyl, both.
Which of the following proteinaceous states?
So that's one of the things that kind of causes people some confusion, the protonation stuff, because like they're thinking like protons and things like that. A hydrogen atom is just like in the nucleus is just a proton.
Yeah.
And then it's got one electron. So if you pull that electron, it's just a proton. And so when we talk about protonation states, it's just adding or removing a hydrogen.
And so my guess is that we have to go to this figure 1 and look at the pKa's. Is that?
Yeah, gonna have to use figure 1. But also they're asking about when the captopril's inhibition is maximized.
Yeah.
So we're probably gonna have to use table 1 as well.
Yeah. And when captopril's inhibition of ACE is maximized, that means that IC50 is going to be lower because it's working really, really well. So It's in that pH range of 3.8 to 9.5. Yeah. Walk me through taking that information from the table and then looking at those pKa's.
So I know that the pH range where this is most powerful is between 3.8 and 9.5, which is between the things that they give us in figure 1. So it's going to be higher than one of these. It's going to be the pH is going to be higher than the pKa for carboxylic acid. It's going to be lower than the pKa for the sulfhydryl group, the SH group. Yep. So just off of that, it's probably going to be one's protonated and one's deprotonated. Which one's which? Maybe I'm not super confident with, but if it was like below both of them, they're both going to be the same. If the pH was above both of them, they would both be the same. And so just from that, I'm thinking it's probably A or B at that point. Now, a lot of times students struggle a little bit with this, but I think the easiest way to think about like trying to figure out like, is it going to have hydrogens on it or not at these different pHs is to think what's going to happen at the lowest pH. If there's like an infinite trillions, billions, quadrillions of hydrogens, everything's going to have a hydrogen on it. At a really low pH, the water is just full of hydrogens. And so at a pH of 1, all of these things are going to have hydrogens on them. Okay. And then as we remove hydrogens from there, aka we raise the pH by removing the hydrogens are going to start to fall off this molecule.
Okay.
So after we pass a pH of 3.7, the hydrogens are going to start to fall off the carboxylic acid. And then, so that'll be deprotonated, but the sulfhydryl will still be protonated. And then as I go above 9.8, then the hydrogens will fall off of that also. And so then everything will be deprotonated.
I like the way of thinking like that.
Yeah, just thinking kind of like at low pH, like everything's got hydrogens on it, right?
Just bathed in hydrogens. And as you increase the pH, those hydrogens are falling off, and then use the pKa's to determine where they're falling off sooner rather than later.
Those are the turning points.
And so then the question is just making sure that you understand the language of what these things are. So I'm assuming that's the carboxylic group or carboxyl group that's deprotonated. So the answer choice would be B.
Yep. Very good.
Okay. Good. I like the thinking. I'm a very kind of visual 3D, let me picture it kind of person, and not everyone is like my wife. Certainly is not like that at all.
No, some people just want to be given like a list of equations and a set of definitions, and I've found that that's not really good for a lot of people, which is why I use analogies all the time. Yeah. It's like the sea of hydrogens and Bug's Life, right? That's a good one.
Bug's Life, yeah.
The Apple Store. You're the Samsung employee.
Yes. All right. Question 26. According to the data in Table 1, What mass of captopril must be dissolved in 3 liters of plasma at pH of 7.4 to inhibit 50% of ACE enzyme activity in vivo? Assume an equal volume of distribution. All right. So then answer choice A, 7.9, was that picograms? Answer choice B, 7.9 nanograms. Answer choice C, 7.9, is that micrograms?
Yep.
And then D, 7.9 grams. So we're all given 7.9, all weights, just varying weights there. And then the graph itself, or the table, if we go back to the table, those are all in micromoles for the IC50. And so it's saying what mass of captopril must be dissolved in 3 liters of plasma at pH of 7.4. So we're given the pH range here for 7.4 is that 0.012 plus or minus the 0.004 micromoles. So I'm assuming we use that data, the 0.012 micromoles of captopril for the IC50. And so we are given 3 liters. And so we need to make sure that we put enough captopril in to get back to that 0.012 into that 3 liters.
Yeah. So just kind of like looking in terms of the units, we have 3 liters, and you've already told me I know we're going to need the 0.012 micromolar, which is moles per liter. So we have moles per liter, we've got liters, we can get to moles pretty quickly from that. But the answer here is in grams.
In grams. And we're given captopril's weight of 217.29 grams per mole.
Right. So if we multiply 3 liters times whatever moles per liter, the liters cancel out and we're left with moles. If we take that times grams per mole, the moles will cancel out and we're left with grams. And so the answer to this one is just multiply all 3 of those numbers together. So you have 3 liters times 0.012 micromolar times 217 grams per mole, which I'm probably going to round to 220 because I'm lazy. And to be honest, I'm not even really that worried about that anyway, because my answer is going to come out to be 7.9.
7.9 something.
It's just times 10 to the whatever.
Yeah.
And so if you set this up, you have 0.012, that's times 10 to the negative 6th moles per liter when you convert it from the micromolar. You times it by 3 liters and times it by 220 grams. You get 7.9 times 10 to the negative 6th grams, which is micrograms.
Micrograms, yeah.
So that's it. That IC50 table, I know that ends up causing a lot of difficulty for students the first time they see it, but they do tell you what it means, right? It's this minimum plasma concentration needed to inhibit 50%. I say it oh, that makes sense. You have students that's going to have to maybe read over that sentence a couple of times to try to understand what the heck it means. But once you've got a good kind of grasp on it, you just understand it's how much of the drug we need to shut down the enzymes.
Yep.
A small amount means it's a really powerful drug. Yeah. So that's it for our potentiometric titration.
Yeah. Thank you. See you. Never want to see you again.
Yeah.